I've got two very simple applications to the Fourier transform that I want to show you today. The first is on the right. This is dual tone multi-frequency signaling. Every phone has a touchpad in some sense. Smartphones have smarter touchpads, I guess, but when you push a key, it makes two frequencies that are unique to that key. So I'm going to play this DTMF, dual tone multi-frequency dialing, for you in case you haven't heard it before. Okay, so I think we've all heard that. And when you push, let's say, a 1, so I'm looking at this table or this matrix in Wikipedia. When you push a 1, so let's hear what a 1 sounds like. All right, that's a 1. If you're musically inclined, then you may have heard two frequencies there. And a 1, the two frequencies that you hear are 697 hertz and 1209 hertz, and that combination of frequencies is unique to a 1. If I push a 2, then I get a different combination. Let's listen to that. All right. A 2 then is that 697 hertz, but also 1336 hertz. And so you can see all the different keys in this table and the different combinations of frequencies that they exhibit when you push the button. So in particular, I'm going to show you the waveform of a 7. So here's a 7. Okay, a 7, according to this table, has frequencies 852 hertz and 1209 hertz. So I've got that for you. Here's the waveform. So I've done the analysis for you already. So when you push a 7, this is the waveform that gets sent out, what you just heard from the 7. And there are two frequencies here, and you can kind of see it in this plot. You have this signal that's kind of oscillating a little bit more slowly, right? And then on top of that, you have one that's going a little bit faster. And so those two superimpose to give you this signal. And the idea is that you want to be able to communicate to the person on the other end which numbers it is that you are pushing. Okay, so when you push a 7 on your touchpad, this signal is audible, and that audible signal gets sent through your microphone. Then your microphone picks it up, and then it gets transmitted to the person on the other end, usually a robot. And that robot then decodes the signal, and then from that decoding determines what number or what key you've pushed. And the chip that does that is this guy here. Let me bring that up. Yeah. So the chip that does that is this DTMF, dual tone multi-frequency chip, and this chip is in just about every phone. So the way this works is that the signal comes in, and then the chip takes the Fourier transform of the signal, and then decodes the frequencies, looks at the Fourier transform of the signal, and gets the two peak frequencies. And then, based on those two peak frequencies, compares it to this table using some digital logic, and then outputs the key that was pushed. That's how it works. Pretty neat, right? And so, what we can do is look at the Fourier transform of this signal, and I've done that analysis for you as well. And this is what you get when you do the Fourier transform. Let me bring it up. Right here. So this is the Fourier transform, and remember, according to that table, the 7 was 852 hertz and 1209 hertz. And so we look at this Fourier transform, and yep, there's the 852 hertz right here. We have a peak there, and we have the 1209 hertz right here, 1209. So this is what that chip would decode. Now, you might ask, well, why is it that you have energy over here? Why is it spread out a little bit? Why isn't it just an impulse at those two frequencies? Because you really don't have frequencies anywhere else. Well, you have to remember the difference between aperiodic and periodic signals. The signal that was sent had a beginning and it had an end. And so in the true definition of periodicity, the signal that was sent was not periodic. And so what you have is this kind of spreading out of energy around those major peaks of 852 and 1209. So even though you have that, it's kind of like an artifact of the beginning and the end. And even though you have that spreading out or that artifact, you can still, of course, determine which frequencies are being sent. You just have your algorithm look at the two peaks of the Fourier transform, and you find the location of those two peaks, and then you compare it to that table, and then you've got the key that was, or the touchpad key that was sent. All right. So in my next demonstration or application that I want to show you, this was some work that two students, Jeremy and Frank, did for me. They were working with me and Stevens Institute of Technology in New Jersey, and what they did was they deployed hydrophones, which are like microphones, into the water and recorded many different types of ships passing by and the noise that they made in the water. And the idea was, could you determine which type of ship it was based on the noise it made in the water? And so there's a lot of theory here, but if we go to the results, these waveforms on the left, these are the signals, and you can't really tell much by looking at the time-based signals. One's a ferry and one's a fishing vessel. What you do is you take the transform of the signal, and so now you've got, here's the ferry Fourier transform, and it's the magnitude, and here's the fishing vessel magnitude of Fourier transform. And then you see the peaks in the Fourier transform are at different locations. Okay, this guy's peak, the fishing boat, has higher frequencies. Its peak is higher in the spectrum, and the ferry has lower frequencies. Its peak is lower in the spectrum. And the reason for that is because of cavitation. Basically, the noise or the frequencies that are generated by the ship depend on the number of propellers, the length of the screw, the size of it, and so forth. So the ferry and the fishing vessel have different characteristics, and so they generate different frequencies. And so you take the Fourier transform, and then you can send the Fourier transform to an algorithm, like a machine learning algorithm, and the algorithm can automatically determine which type of ship it is that is passing by. Pretty neat.